artist's impression of the merger of two neutron stars. University of Warwick. Mark Garlick. In September of 2015, astronomers detected, for the first time, gravitational waves, cosmic ripples that distort the very fabric of space and time. They came from a violent merger of two black holes somewhere in the universe, more than 1 billion light-years away from Earth. Astronomers observed the phenomenon again in December, and then again in November 2016, and then again in August of this year. The discoveries confirmed a century-old prediction by Albert Einstein, earned a Nobel Prize, and ushered in a new field of astronomy. But while astronomers could observe the effects of the waves in the sensitive instruments built to detect them, they couldn't see the source. Black holes, as their name suggests, don't emit any light. To directly observe the origin of gravitational waves, astronomers needed a different kind of collision to send the ripples Earth's way. This summer, they finally got it. Scientists announced Monday they have observed gravitational waves for the 5th time, and they've seen the light from the cosmic crash that produced them. The waves came from the collision of two neutron stars in a galaxy called NGC 4993, located about 130 million light-years from Earth. Neutron stars are strange, mysterious objects, the collapsed cores of stars that exploded in spectacular fashion, supernovae, and died. These stars measure about the size of a metropolitan city, but have about the same mass as our Sun. Astronomers had long predicted that when two neutron stars collide, the resulting explosion would produce electromagnetic radiation, in the form of optical light. The afterglow would shine bright enough to be seen through powerful telescopes, the first visible proof of a source of gravitational waves, provided the latter could also be detected. Here it is, captured by the European Southern Observatory's Very Large Telescope in Chile, in the center of the image. ESO AJ11NR Tanviru. Astronomers made the observation August 17. 3 gravitational wave detectors, 2 at the Nobel Prize-winning Laser Interferometer Gravitational Wave Observatory LIGO in the United States, and 1 at the Virgo Interferometer in Italy, detected the cosmic ripples as they washed over Earth. About 2 seconds later, 2 space telescopes, NASA's Fermi Gamma Ray Space Telescope and ESA's International Gamma Ray Astrophysics Laboratory, observed a short burst of gamma rays, the most energetic wave in the electromagnetic spectrum, coming from the same part of the sky. The almost simultaneous detections caught astronomers' attention, and they threw everything they had at it. Dozens of ground-based telescopes around the world quickly turned their gaze toward the same slice of sky. ESO's army of telescopes, sprinkled across the Chilean desert, scanned through the night. When the sun set in Hawaii, the Pan-STARRS and Subaru telescopes joined in. So did space observatories like Hubble. Within hours, astronomers pinpointed the location of the collision using an ESO telescope that sees in infrared wavelengths. They aimed the SWAP-A telescope, also in Chile, at the region and started snapping pictures. They found the afterglow in the 9th shot. Astronomers observed the afterglow of the merger for days. They watched as the glowing orb faded and changed colors from blue to red, a telltale sign that the remnants of the crash were pushing radioactive material out and cooling down. Here's an animation from ESO that shows 2 neutron stars spiraling closer together until they crash. Astronomers examined the gravitational waves to estimate the size of the colliding objects and found they had masses far smaller than black holes. The biggest neutron star is a lot smaller than the smallest black hole, said Richard O'Shaughnessy, a theoretical gravitational wave astrophysicist at Rochester Institute of Technology, who works in the LIGO group. The mass measurement, coupled with the near-simultaneous observations of the gravitational waves in a light source, told scientists they were dealing with neutron stars. The event was also much closer to Earth than previous mergers recorded by LIGO, which originated between 1 billion and 3 billion light-years away. All told, about 70 observatories captured the event, named GW170817 for the day it made itself known to Earth. The collision's aftermath was recorded at nearly every wavelength. O'Shaughnessy described the discovery as a Rosetta Stone for astronomy. The observation produced streams of data with richness seemingly unprecedented for a single astronomical event. The findings, which are spread across many papers in several journals, provide evidence for several theories in astronomy. The discovery supports the theory that neutron star collisions produce short gamma-ray bursts, brief streams of light that shine brighter than 1,000,000 trillion times the Sun. Gamma-ray bursts have been detected and imaged before, but without gravitational wave detectors like LIGO and Virgo, astronomers couldn't know whether they came from cosmic collisions. The presence of the short gamma ray burst suggests the merger led to a kilonova, a powerful explosion 1,000 times brighter than a supernova. Astronomers have long suspected kilonovae follow neutron star collisions, spewing material out into space. In the case of GW170817, scientists estimate the kilonova ejected material at 1/5 the speed of light, faster than a typical supernova. The findings support another prediction that neutron star collisions produce chemical elements heavier than iron, like gold and platinum. Astronomers believe neutrons released during the merger combine with surrounding atoms in a phenomenon known as R-process nucleosynthesis. Telescope observations of GW170817's spectra, the chemical composition of the star material, revealed it contained heavy elements, including 10 times the mass of the Earth in gold, according to O'Shaughnessy. These kinds of collisions, astronomers believe, may be responsible for populating the universe with heavy elements. The discovery gave scientists a chance to measure the expansion of the universe, too. Since astronomers knew which galaxy the latest gravitational waves came from, they could calculate the distance between that galaxy and Earth and then plug it into equations for the rate of expansion, known as the Hubble constant. Good news, the answer matched up with previous estimates from other methods. When scientists announced their fourth detection of gravitational waves in August, they promised that these kinds of announcements would become routine. LIGO and Virgo's instruments, they predicted, will detect the rippling of space-time once and multiple times a week. It's a certainty that we will experience the effects of mergers between black holes and neutron stars, and maybe between one of each, again. LIGO and Virgo scientists may even have a few confirmed detections they haven't told us about yet. And the more, the better. This reign of events will continue at such a high rate that we'll have a census of comic explosions, O'Shaughnessy said. And by data mining the census, we can learn something about how they form, about the origins of these mysterious events.